Composition. The overall structure of the charted regions of the solar system consists of the Sun, 4 smaller inner planets surrounded by a belt of mostly rocky asteroids, and 4 giant planets surrounded by the Kuiper belt of mostly icy objects. Astronomers sometimes informally divide this structure into separate regions. The inner solar system includes the 4 terrestrial planets and the asteroid belt. The outer solar system is beyond the asteroids, including the 4 giant planets. Since the discovery of the Kuiper belt, the outermost parts of the solar system are considered a distinct region consisting of the objects beyond Neptune. The principal component of the solar system is the Sun, a low-mass star that contains 99.86% of the system's known mass and dominates it gravitationally. The Sun's 4 largest orbiting bodies, the giant planets, account for 99% of the remaining mass, with Jupiter and Saturn together comprising more than 90%. The remaining objects of the solar system, including the 4 terrestrial planets, the dwarf planets, moons, asteroids, and comets, together comprise less than 0.002% of the solar system's total mass. The Sun is composed of roughly 98% hydrogen and helium, as are Jupiter and Saturn. A composition gradient exists in the solar system, created by heat and light pressure from the early Sun. Those objects closer to the Sun, which are more affected by heat and light pressure, are composed of elements with high melting points. Objects farther from the Sun are composed largely of materials with lower melting points. The boundary in the solar system beyond which those volatile substances could coalesce is known as the frost line, and it lies at roughly 5 times the Earth's distance from the Sun. The objects of the inner solar system are composed mostly of rocky materials, such as silicates, iron or nickel. Jupiter and Saturn are composed mainly of gases with extremely low melting points and high vapor pressure, such as hydrogen, helium, and neon. Ices, like water, methane, ammonia, hydrogen sulfide, and carbon dioxide, have melting points up to a few hundred kelvins. They can be found as ices, liquids, or gases in various places in the solar system. Icy substances comprise the majority of the satellites of the giant planets, as well as most of Uranus and Neptune, the so-called ice giants, and the numerous small objects that lie beyond Neptune's orbit. Together, gases and ices are referred to as volatiles. Distances and scales. The astronomical unit, 150 million kilometers, 93 million miles, would be the distance from the Earth to the Sun if the planet's orbit were perfectly circular. For comparison, the radius of the Sun is 0.0047 astronomical units, 700,000 kilometers, 400,000 miles. Thus, the Sun occupies 0.00001%, 10⁻⁵%, of the volume of a sphere with a radius the size of Earth's orbit, whereas Earth's volume is roughly 1/1,000,000th, 10⁻⁶, that of the Sun. Jupiter, the largest planet, is 5.2 astronomical units, 780 million kilometers, 480 million miles, from the Sun and has a radius of 71,000 kilometers, 0.00047 astronomical units, 44,000 miles, whereas the most distant planet, Neptune, is 30 astronomical units, 4.5 times 109 kilometers, 2.8 times 109 miles, from the Sun. With a few exceptions, the farther a planet or belt is from the Sun, the larger the distance between its orbit and the orbit of the next nearer object to the Sun. For example, Venus is approximately 0.33 astronomical units farther out from the Sun than Mercury, whereas Saturn is 4.3 astronomical units out from Jupiter, and Neptune lies 10.5 astronomical units out from Uranus. Attempts have been made to determine a relationship between these orbital distances, like the Titius-Bode law and Johannes Kepler's model based on the Platonic solids, but ongoing discoveries have invalidated these hypotheses. Some solar system models attempt to convey the relative scales involved in the solar system on human terms. Some are small in scale, and may be mechanical, called orreries, whereas others extend across cities or regional areas. The largest such scale model, the Sweden solar system, uses the 110-meter, 361 feet, Avicii Arena in Stockholm as its substitute Sun, and, following the scale, Jupiter is a 7.5-meter, 25-foot, sphere at Stockholm Arlanda Airport, 40 kilometers, 25 miles, away, whereas the farthest current object, Sedna, is a 10 centimeters, 4 in, sphere in Luleå, 912 kilometers, 567 miles, away. If the Sun-Neptune distance is scaled to 100 meters, 330 feet, then the Sun would be about 3 centimeters, 1.2 in diameter, roughly 2/3 the diameter of a golf ball, the giant planets would be all smaller than about 3 millimeters, 0.12 in, and Earth's diameter along with that of the other terrestrial planets would be smaller than a flea, 0.3 millimeters or 0.012 in, at this scale. Sun. The Sun is the solar system's star and by far its most massive component. Its large mass, 332,900 Earth masses, which comprises 99.86% of all the mass in the solar system, produces temperatures and densities in its core high enough to sustain nuclear fusion of hydrogen into helium. This releases an enormous amount of energy, mostly radiated into space as electromagnetic radiation peaking in visible light. Because the Sun fuses hydrogen into helium at its core, it is a main sequence star. More specifically, it is a G2 type main sequence star, where the type designation refers to its effective temperature. Hotter main sequence stars are more luminous. The Sun's temperature is intermediate between that of the hottest stars and that of the coolest stars. Stars brighter and hotter than the Sun are rare, whereas substantially dimmer and cooler stars, known as red dwarfs, make up about 75% of the stars in the Milky Way. The Sun is a population I star. It has a higher abundance of elements heavier than hydrogen and helium, metals in astronomical parlance, than the older population II stars. Elements heavier than hydrogen and helium were formed in the cores of ancient and exploding stars, so the first generation of stars had to die before the universe could be enriched with these atoms. The oldest stars contain few metals, whereas stars born later have more. This higher metallicity is thought to have been crucial to the Sun's development of a planetary system because the planets form from the accretion of metals. Environment and habitability. Outside of the main part of the Sun's atmosphere extends the heliosphere and dominates the solar planetary system. The vast majority of the heliosphere is occupied by a near vacuum known as the interplanetary medium. Along with light, the Sun radiates a continuous stream of charged particles, a plasma, called the solar wind. This stream of particles spreads outwards at speeds from 900,000 km per hour, 560,000 miles per hour, to 2,880,000 km per hour, 1,790,000 miles per hour, creating a tenuous atmosphere that permeates the interplanetary medium out to at least 100 astronomical units, 15 billion km, 9.3 billion mile, C-section heliosphere. Activity on the Sun's surface, such as solar flares and coronal mass ejections, disturbs the heliosphere, creating space weather and causing geomagnetic storms. The largest structure within the heliosphere is the heliospheric current sheet, a spiral form created by the actions of the Sun's rotating magnetic field on the interplanetary medium. Earth's magnetic field stops its atmosphere from being stripped away by the solar wind. Venus and Mars do not have magnetic fields, and as a result the solar wind is causing their atmospheres to gradually bleed away into space. Coronal mass ejections and similar events blow a magnetic field and huge quantities of material from the surface of the Sun. The interaction of this magnetic field and material with Earth's magnetic field funnels charged particles into Earth's upper atmosphere, where its interactions create aurorae seen near the magnetic poles. The heliosphere and planetary magnetic fields, for those planets that have them, partially shield the solar system from high-energy interstellar particles called cosmic rays. The density of cosmic rays in the interstellar medium and the strength of the Sun's magnetic field change on very long timescales, so the level of cosmic ray penetration in the solar system varies, though by how much is unknown. The interplanetary medium is home to at least two disk-like regions of cosmic dust. The first, the zodiacal dust cloud, lies in the inner solar system and causes the zodiacal light. It may have been formed by collisions within the asteroid belt brought on by gravitational interactions with the planets. A more recent proposed origin is the planet Mars. The second dust cloud extends from about 10 astronomical units, 1.5 billion km, 930 million mile, to about 40 astronomical units, 6.0 billion km, 3.7 billion mile, and was probably created by collisions within the Kuiper belt. The zone of habitability of the solar system is located in the inner solar system. Beside the solar conditions for habitability on solar system objects such as Earth, habitability might be possibly in subsurface oceans of various outer solar system moons. Inner solar system. Stay tuned for part 3.